Thank you so much for the introduction. So yes, my name is Jasmine Brewer, and I'd like to thank you all for coming today and spending your Saturday to hear me talk a bit about my research, and in particular to try to explain what I mean by this liquid state of quarks and gluons. So the matter that we see around us is often sort of a very complex composition of much simpler objects. So the chair that you're sitting on, maybe it's made of wood. So at the basis of that is some, strings of cellulose molecules. Those molecules are themselves composed of atoms like oxygen and carbon. And at the center of those atoms, in the nucleus, are particles like protons and neutrons. And inside protons and neutrons are the particles which we actually consider fundamental, which are quarks and gluons. And the way that you can think about heating up matter is that as the temperature gets higher and higher, sort of more and more complex objects become unstable. So if you imagine heating up this chair, at some point, these long strings of molecules would start to break down into something simpler like carbon. And in the sun, for example, is so hot, so this is kind of the hottest place in our universe, it's so hot that only sort of the simplest atoms are stable, like helium and hydrogen. And actually, if you go to the center of the sun, these have often also lost their electrons, and so they're essentially protons and neutrons. And so one of the kind of fundamental questions that you can ask from this picture is if the hottest place in our sun, or in our universe is the sun, what would it actually take to melt these protons and neutrons into their fundamental constituents, these quarks and gluons? And it turns out that there actually was a point in the universe where all matter was in the form of where protons and neutrons weren't stable, and all matter was in the form of these quarks and gluons. So here I'm showing a picture of the evolution of the universe from the time of the Big Bang all the way to the present day. And actually in the first microsecond after the Big Bang, protons and neutrons weren't yet stable. And so all of the matter in the universe was actually in this liquid state of quarks and gluons. But the universe was expanding and cooling very quickly. So after a microsecond, these quarks and gluons turned back into protons and neutrons. After 380,000 years, the cooling had happened enough that the simplest atoms could form, like hydrogen. And today we know that we experience in our daily lives much more complex atoms and also molecules. And so today the only way that we can actually recreate these very extreme conditions where protons and neutrons aren't stable is actually in high energy collider experiments. So the Large Hadron Collider, which is based in Geneva, is the biggest particle accelerator in the world. It's about 27 kilometers around. And most of the time at the Large Hadron Collider, they're colliding protons. And so you can imagine that these protons go around in this 27-kilometer ring in tunnels that look like this, which are buried underground. And so at some special points along the ring, they take protons going one way and protons going the other way, and they collide them. And the places that they do this are in these 4 special interaction points where there are experiments which are designed to measure the output of these collisions. And so when you collide protons at high energies, you can kind of think of them essentially as breaking apart. So what it looks like when you collide a proton with another proton is that basically you'll collide, say, a quark from one of the protons with a gluon in the other one. And so essentially you can think of these interactions as a collision between a quark or a gluon from one proton and a quark or a gluon from another proton. And these collisions can produce a wide variety of different types of particles, so both, quarks and gluons, but also electrons, and then even more exotic particles that you might have heard of, like the Higgs boson or the W boson. And so one of the big goals of this program is to sort of both produce these particles and also study how they interact with one another so that we can really confront our theoretical understanding of these types of particles and their interaction. But even though we can produce all of these types of particles, kind kind of by far the largest contribution to the particles which are produced, since protons are themselves sort of composed of quarks and gluons, most of the time we're producing also quarks and gluons. And so unless you ask for something specific, in general, you'll see a lot of production of these particles which are associated with the strong force. And so I'll be mostly talking today about the production of quarks and gluons and the strong nuclear force. But protons aren't the only thing that we collide at the Large Hadron Collider. You can also collide heavy nuclei, for example, lead. And for this purpose, you can essentially think of lead as just being a giant bag of 82 protons and 126 neutrons. And so when you collide two lead atoms, you essentially get a huge number of proton-proton collisions, which all happen in a very small region of space, essentially at the same time. And because you have so many of them all at the same place, actually something kind of fundamentally different happens in these collisions than what happens in proton-proton collisions. So in particular, the energy density or the temperature in that tiny region of space is so high that actually protons and neutrons do become unstable. And so we produce in that region of space the hottest temperatures in the universe, which essentially produce this unique state of matter where quarks and gluons are actually free. And this state of matter is called the quark-gluon plasma, which is what I'll be kind of talking about today and what a lot of my research focuses on. And just to give you a sense of the types of scales that we're talking about, the temperature which is created in this interaction region of these nuclei is 250,000 times the temperature at the core of the sun in a size which is 10,000 times smaller than an atom. So these are really, really extreme environment where we can produce this unique material. So one of the reasons that the quark-gluon plasma is so fascinating is that quarks and gluons are very strange particles. So for the ordinary types of forces that you experience around you, in general, the strength of the interaction will decrease with distance. So for example, if you think about electricity and magnetism, if you hold two magnets close together, then you'll feel them attracting a lot, and then as you pull them apart, the attraction between them will start to decrease. And this is completely the opposite for quarks and gluons. So if you could hold two quarks in your hands, when they were close together, you wouldn't feel much interaction between them. But as you pull them apart, the interaction gets stronger and stronger and stronger. And in fact, it gets so strong that you actually can't pull them apart at all. And so this is what leads to them becoming confined in bound states like protons and neutrons before you can really pull them apart. So this is the essential reason why we don't observe free quarks or gluons in the world around us. And so because quarks and gluons have such strange interactions, it's really fascinating to try to understand what would be the properties of a material which is composed of many of these quarks and gluons. You know, would they interact strongly with one another? Would they interact weakly? And in fact, because quarks and gluons interact weakly when their distance separation is small, many people thought that when you create this dense material in a small space, that would actually be essentially a gas, where those particles would interact weakly with one another. But in fact, one of the kind of fascinating outcomes of the heavy ion physics program has been that it's actually completely the opposite. So this material which we produce is actually the most strongly interacting fluid which has ever been observed. And so this is a really sort of exciting avenue to kind of study this completely novel state of matter. So I hope I've convinced you that the quark-gluon plasma is interesting, but one of the issues is that it's also very challenging to study. And the reason that you can kind of imagine this is that it's produced in a very small place and for a very short time. And so very quickly after the collision, these quarks and gluons turn back into bound states like protons and neutrons and other stuff, pions and kaons. And then those particles are what flies along for a while until we can measure it in a detector. And because we have so many proton-proton collisions occurring at the same time, the energy density and the temperature is so high, we also produce a huge number of particles. So what I'm showing here is an event display from one of the experiments at CERN for a single collision of two nuclei. And all of these sort of rainbow colors in the center are all individual particles which are produced in this event. So you can imagine that digging out some detailed understanding about this material from that huge collection of particles is not always easy. So when I tell you that this is a strongly interacting liquid, how do we actually know that? How have we measured it? So the essential kind of, in some sense we get lucky, which is that actually kind of the dynamics of a liquid tell us quite a lot about the underlying interactions between the constituents that form that liquid. So to try to explain that a bit, imagine that you have some liquid, for example, the quark-gluon plasma, but it can be anything, which has a squished geometry, so it's shorter along one direction than along the others. Then if these particles in this material aren't really interacting much with each other, then the way that this is going to expand will be equally quickly in all directions. So this is kind of a characteristic feature of gases. On the other hand, if these particles do interact strongly with one another, then actually this will generate an anisotropy in the pressure, where there will be higher pressure along the short direction and lower pressure along the long direction. And this will drive the system to expand more quickly along the short direction than it does along the long direction. And actually, it turns out that in most cases in heavy ion collisions, we actually do produce a quark-gluon plasma which is spatially deformed. And you can see this because you can imagine if you take nuclei, which here are represented as circles, and they collide a little bit off-center with each other, then the region where they overlap, which is what's shown in pink, actually has this kind of almond shape where it's a bit asymmetric. And so then we can actually measure the particles which are produced in these collisions, and we can actually find that the correlations between particles produced in these collisions indicate that they're actually expanding more quickly in one direction than in others, and this allows us to understand that this is a fluid undergoing this pressure-driven expansion, indicating strong interactions. But to get more quantitative, we can actually also access the viscosity of the quark-gluon plasma from experiments. So viscosity is a really key feature of fluids, which basically tells you how efficiently it flows around objects. So the quintessential example is that honey has a large viscosity, while something like water would have a low viscosity. And one of the kind of curious or perhaps non-intuitive features of viscosity is that actually, as you have stronger interactions between the constituents in a fluid, actually the viscosity decreases. And so the way that we can try to measure viscosity of the quark-gluon plasma is by running hydrodynamic simulations of the evolution of a heavy ion collision. And then a viscosity is the parameter which goes into these hydrodynamic simulations. And then by comparing the output of these simulations to particles which we measure experimentally, we can constrain the values of that parameter. And so here I'm showing a plot of the shear viscosity with a ratio to the entropy density for the quark-gluon plasma extracted in this way as a function of temperature. And so by itself, maybe it's not completely clear what you should take away from this number. So now I want to show this same curve. So this curve, which we're looking at now in blue, shows up now in orange on this picture in comparison to the shear viscosity of many other common liquids. So here you see the shear viscosity of water in blue and superfluid helium in green. And what's kind of remarkable is that the viscosity of the quark-gluon plasma is much lower than the viscosity of any of these other liquids, and in fact, than any other liquid which has ever been observed. And in fact, so quantum mechanics, it turns out, actually predicts a lower bound on the shear viscosity for any physical quantum fluid. And that's what's shown here in this dashed black line. And so what we see is that not only is the quark-gluon plasma lower viscosity than any other fluid, but in fact, it's essentially the lowest viscosity liquid that's allowed by quantum mechanics. And so this kind of also means, since low viscosity liquids tend to have strong interactions, that these quarks and gluons are interacting really almost as strongly as they can in this liquid, consistent with quantum mechanics. So, I've been talking so far about the viscosity, but viscosity is not the only parameter that we might care about the quark-gluon plasma. So hydrodynamics is an effective theory which tells us how systems behave when they're relatively close to equilibrium. But recently, people have become very interested in also understanding how this system behaves also when it's further out of equilibrium. So here I'm showing, again, sort of the time evolution of a heavy ion collision, but now with a more detailed view of sort of the process which leads to the formation of the quark-gluon plasma itself. So here you can see the nuclei collide. And then, as I was telling you at the beginning, you kind of have a case where you have a bunch of proton-proton collisions, which happen essentially independently from one another. And so if you look at the energy density for that state, it's really, really spiky, because you just have a bunch of collisions which are relatively uncorrelated. But then these quarks and gluons, they interact a lot and they radiate a lot. And so very quickly, these very spiky energy densities starts to smooth out, and you get a state which is sort of approaching equilibrium. And then at some point, it's sort of close enough to equilibrium that we can describe sort of the subsequent evolution with hydrodynamics. And this sort of phase, the process of equilibration, which leads to the formation of this liquid, also holds a lot of information about what are the underlying dynamics inside the liquid. So for example, it was shown that if quarks and gluons interact with one another very weakly, then actually the process which leads to thermalization happens through turbulence. And there's been a lot of interest in understanding, in the more realistic case that these interactions are stronger, what are kind of the general features of this process of equilibration that would hold. Okay, so I started on this topic by saying, okay, we have this plasma, which is very, very small, and it's challenging to actually find ways to measure its properties. And so we got a little bit lucky here, and we said, okay, because of some properties of liquids, we can measure correlations of these relatively low momentum particles and actually access the liquid properties of the quark-gluon plasma. But the question is, what other information, what other strategies might we use to try to measure it? So historically, a very kind of important way to try to measure the properties of a material is essentially by shooting high energy particles at it and seeing how they deflect through their interactions with the quark-gluon plasma. So a famous example of this that you might have be familiar with is that, when they were trying to understand the structure of atoms, there were kind of two competing models, either sort of the plum pudding model where all of this matter was essentially uniformly distributed inside of the atoms, or the Rutherford model where all of that matter was essentially concentrated in this dense nucleus. And so the way that they tried to address this is shoot high energy particles at this thing, and then what they measured is that these high energy particles actually had large deflections, which weren't consistent with this kind of plum pudding model, and this led to the discovery of the nucleus inside of the atom. So ideally, we would like to do something similar with the quark-gluon plasma. We would like to shoot high energy particles at it and use their deflection to study how quarks and gluons are actually oriented inside of this material. But the problem is that this quark-gluon plasma is much too short-lived to actually achieve this using any sort of external particles to the collision itself, because the total lifetime of the quark-gluon plasma is 1,000 times shorter than the fastest laser pulses that might provide particles that we could study it with. But fortunately, we do have some recourse, which is that, so proton-proton collisions, when they happen, you very often, as I was describing at the beginning, have a very high energy interaction, say between one quark or gluon and one proton and a quark or gluon and the other proton. And if this interaction is very high energy, it produces essentially sprays of high energy particles, which we call jets. And so these, in a detector, jets might look like these blue towers of collimated sprays of particles, which are kind of back-to-back with one another. And in heavy ion collisions, as I said, you have many, many, many proton-proton collisions, and a lot of these are relatively low momentum, and those are kind of mainly contributing to forming this plasma itself. But you can also have occasional interactions in the same way you do in proton-proton collisions, where you have a very high energy transfer, and this produces jets. And the difference between jets in heavy ion collisions and jets in proton-proton collisions is that in heavy ion collisions, these jets are produced inside of the quark-gluon plasma, and then they have to essentially plow out through it before you can measure them. And so then by measuring essentially how jets are modified in heavy ion collisions compared to proton-proton collisions, we can try to access sort of the properties of the medium through their interaction with jets that leads to this modification. So just to kind of summarize again, what we wanted to do was to shoot high energy particles at it, but since that's not possible, instead we use these high energy sprays of particles which are produced inside. And this provides a really key signature for the formation of the quark-gluon plasma and also an avenue to study it. So in fact, this effect is fairly large. So there's about half as many jets in heavy ion collisions of a particular energy as you would expect from proton-proton collisions. And then they also have other modifications, for example, increased imbalance in the momentum between jets which are produced back-to-back. And so this is really exciting because it means that these actually do interact substantially with the quark-gluon plasma, and therefore that they really give us an avenue to try to study the quark-gluon plasma using these objects. So in order to kind of dig a little bit deeper and try to understand the quark-gluon plasma in a bit more detail, we also have to really understand jets. And the reason that you can understand this is if you're trying to study the atom by shooting particles through it, you would really like to know what you're shooting at it and what energy they have. And since these are produced inside the collision, we have much less control over that than we would in an ordinary type of experiment. So jets are complex objects which are built out of quarks and gluons, but at a basic level, building a jet is fairly simple. There's only three things that can happen to quarks and gluons. You can have a quark which splits to a quark and a gluon. You can have a gluon which splits to two gluons, and you can have a gluon that splits to two quarks. And jets are essentially a composition of these basic building blocks. So here I'm showing just one example of how a high energy quark might split into other quarks and gluons. And once they reach sort of low enough scales, those quarks and gluons will again become bound in hadrons, protons and neutrons and pions, and those are what ends up as these sprays of particles in the detector. But what you can already see from here is that even with these three building blocks, there's a huge variety of jets that you can actually compose by assembling these different building blocks. And this is both kind of an advantage, but also a challenge. Because, as you can imagine, the quark-gluon plasma is just a mess of quarks and gluons. And so each of these different types of jets, depending on how the quarks and gluons are oriented inside of it, can interact differently with this quark-gluon plasma than each other. And so the more information that we can control on what a jet actually looks like, the easier it's going to be for us to use that to study sort of detailed properties of this medium. So as I already kind of alluded to on the last slide, in general, we expect that a quark and a gluon will interact differently with the quark-gluon plasma. The basic reason is that gluons have larger charge than quarks, and so they'll interact more. But the exact amount more which they'll interact is kind of an important property of the medium. And the reason you can think of this is that charge can be screened inside of the medium. And so we are not guaranteed that the ratio of the charges of quarks and gluons is actually the ratio with which they're interacting. So we'd really like to study this part of the medium. But one of the challenges, as I've iterated already before, is that once these quarks and gluons all turn back into hadrons, you don't have any information anymore about what was the way which they were actually produced. But it turns out that there's kind of a cute way where you can anyway actually separate jets which started as a quark from those that started with a gluon despite this. So the idea is that you can kind of essentially imagine that you just classify a jet as whether it was initiated by a quark or initiated by a gluon, and then you can think of all events as just being a big bag of jets, and you know that they were all initiated by a quark or a gluon, but you don't know which one is which. And so this actually kind of ends up being sort of a classical kind of machine learning problem where you can try to distinguish, a bag of jets with one ratio of quark and gluon composition to a bag of jets with a different ratio of quark and gluon composition, and understand from that basically the separate modification of quark-initiated jets and gluon-initiated jets. So this was done first in proton-proton collisions, and then with collaborators, I did this also in heavy ion collisions, which gives us really a method to access the different modification of these types of jets in the quark-gluon plasma. So whether a jet is initiated by a quark or a gluon is a very important feature of its interactions. And the reason you can think about that is that it's what sets the charge of the whole jet because of charge conservation. But of course, you can have many different types of jets which start as a quark or which start as a gluon. So these categories still include many different types of jets. And as I've said, before, the challenge is that you really can't tell these jets apart once you only have hadrons anymore. But there's one special type of exception to this, which is for particular types of particles. For example, quarks that have a large mass, actually they can't be produced during the hadronization process. They're too heavy. And so that means that we can trace. So if we find hadrons which contain these heavy quarks inside of jets, because they can't have been produced in hadronization, we know that they came from the jet itself or from the shower. And so these kind of give us a unique opportunity to actually trace back the history of how a jet formed and really understand which were all of the building blocks that went together in its composition. And so this process is something that I've been working on in several things recently to understand sort of how we can leverage this unique control that we have in these types of cases to really gain a better understanding of the quark-gluon plasma. So finally, I want to just kind of take a step back and try to come a little bit full circle and also give you a bit of a sense of some of the direction of the field. So in the first part of the talk, I discussed sort of how we can use measurements of correlations of flow momentum particles to access sort of the hydrodynamic behavior like the viscosity of the quark-gluon plasma. And then in the second part of the talk, I kind of transitioned to another type of strategy to study the quark-gluon plasma where we use these high energy sprays of particles to kind of probe it. And these are sort of two of the classical kind of strategies which the community has been using to study the quark-gluon plasma. But recently it's become appreciated that, a key aspect of understanding the quark-gluon plasma in detail is also understanding how it behaves in far from equilibrium situations. And so this involves both understanding kind of how it forms after the collision, how it comes to be described by hydrodynamics in this process of equilibration. And it turns out that it's also really key for understanding jet measurements. And the reason that you can kind of think of this is that we've been talking so far as if you have this high energy spray of particles, which is just going through a static thermal bath of stuff. But of course, as you can imagine, if you shoot a bullet through water, you're going to have a major non-equilibrium response of the water in the wake of that bullet. And so we actually have this process also in heavy ion collisions, that when jets go through the quark-gluon plasma, they also leave a lot of non-equilibrium material in the wake, which we aim to understand. And so there's a lot of theoretical effort and also new experiments which are being designed to try to address sort of this intersection of hydrodynamics, equilibration, and also jets in heavy ion collisions. And so there's many, I think, kind of open questions which are helping us to sort of drive the directions of the future. So one of the major questions which we aim to address with jets is to understand how we can try to access this microscopic structure of the quark-gluon plasma using these high energy processes. And as I tried to argue to you today, this really necessitates that we have excellent control over the jets themselves in order to really study the medium using them. And rare processes can hold unique insights for this. So this is one thing for the example which I gave in this talk, where we can use these heavy quarks to kind of pin down the type of jet which we had. And there are also some other types of cases where you can use other particles produced in the event, for example, Z bosons or photons, to gain more information about the event than you would have otherwise. But the disadvantage is that these processes tend to be rare, and so you need a lot of collisions to observe them. So for example, with the, you might observe 500 sort of normal jets for every one jet with, two heavy quarks inside of it. And so this is part of what sort of drives a program for extensive more data collection at the Large Hadron Collider, so that we can gain the statistics which will allow us to use these more rare but also more informative processes to kind of drive our understanding. In addition, as I kind of motivated, we're very interested in understanding these processes of equilibration and the formation of the quark-gluon plasma itself. And one of the challenges historically for doing this is that in heavy ion collisions, which is what I've been talking about this whole time, you do have a significant phase where equilibration is happening, but there's also a really long time where the system is essentially described by hydrodynamics. And so there's been a lot of interest recently in also understanding collisions of smaller nuclei. For example, this is a picture of an oxygen collision, where the process of sort of the whole lifetime of the system is shorter because it's smaller. And so the relative importance of this phase of equilibration compared to the phase of hydrodynamics is more. And so it gives us kind of more emphasis and sort of another eye into this process of equilibration. And so there's a lot of upcoming excitement on new experiments on these other types of collisions where we can try to access this information. And so there's sort of several kind of upcoming experiments, both at the LHC and a smaller running experiment in Long Island, really trying to pin down a lot of these effects and gain also higher statistics. So I'm looking forward to exciting progress in the coming years in this area. So thank you very much for your attention.